All right, and now for the last talk of the day, we have Emil Gjørup talking about congruence closure and cubical type theory. Go ahead.
Thank you. So my plan is to tell you about this project I did where I implemented the congruence closure in cubical type theory. And it is an extension of the work done by Daniel Selsom and Leonardo De Mora, who implemented a congruence closure procedure for intensional type theory of the proof assistant, for the proof assistant lean. And my work is done as a master thesis supervised by Bas Spiros. So my plan for this presentation is to first tell you about this congruence lemma, which is a key lemma needed to implement the procedure. Next, I'll tell you very briefly of how the procedure works in intensional type theory. And next, I will extend this to cubical type theory. And lastly, I will show you which sort of problems behaves the worst for this procedure. So first, the congruence closure procedure is automating proofs that can be constructed using reflexivity, symmetry, transitivity, and then congruence of equality. And it's important to note here that I'm speaking about equality and not equivalence relations in general. And the first procedure implemented for intensional type theory was first presented in 2017 by Selsom and De Mora. Although Koch did have this congruence tactic, but only supported first order equational logic. One limitation of the intensional type theory of the procedure in intensional type theory is they assume an axiom, the uniqueness of identity proofs axiom. So we can't just take the exact same procedure and put it into cubical type theory. So the first problem we have to solve is to implement this congruence lemma, which is a statement saying that functions respect equality, but generalized to be equal functions as well. So to see why this is difficult in intensional type theory, it makes sense to first look at a simpler problem, just that functions respect equality. And since we have dependent functions, this goal equality could be between terms of different type. And we are not able to state that in just plain intensional type theory without new constructions. And just to make matters worse, we have to state this lemma, which is about equal functions and of different type as well, meaning that every equality we have will need to be this heterogeneous equality. And the heterogeneous equality they introduce in the work by Selsom and De Mora is this HEC type, which is defined as an adductive type, similar to the identity type in intensional type theory, just with this extra type for one of the terms, such that the terms can be of different type. And using this, we can state the congruence lemma. However, it turns out to be impossible to prove. And what they do instead is they, on a meta level, generate special case lemmas every time they need this lemma. And they do that for explicit functions. Yeah, and to prove these special case lemmas, they use this axiom again. So we of course have to do something else in cubical type theory. And to talk about the solution we come up with, it makes sense to first talk about how equality works in cubical type theory. I wasn't sure how much to expect people to know about cubical type theory, so I will also give a very simplified introduction to equality in cubical type theory. And the idea is that we treat equality as a function from this unit interval type into some type A. And then the unit interval, the endpoints of this will correspond to the terms in the equality. And then to be able to talk about, to include the endpoints in the type, we introduce this path type, which we will use as our equality. And we also introduce these two special case lambda abstractions just for this interval, these two path abstraction and path application. So these are introduced into the type theory. And just to show you an example of how to use this path abstraction, here's an example of how to define reflexivity, which is just a constant path, and an example of how to use how to define symmetry. I don't think I'll spend more time on this. It sounds like you know more than me about this. So we still need a heterogeneous equality in cubical type theory, and this is just taking the idea a bit further. So now the type can also depend on the unit interval, meaning that now the type itself is a path. So we can define this as a dependent path, such that the endpoints of this dependent path is in different types. And this is the equality I'll use for the rest of this presentation. Yeah, and I use the notation here for dependent path. And just to show you an example of functions respecting equality for dependent functions, we can here state a path between the types as this path abstraction. And then using this, we can actually state and prove the congruence lemma in cubical type theory. And it is surprisingly simple to prove, and there's a lot to read for just the type. But the proof is only this simple path abstraction here. One interesting part is how we define the equality between the two functions. Since we have to deal with the argument, we have to first talk about the types of the arguments being equal, and then talk about the type families being equal as well. Okay, so now for the procedure. So the idea of the procedure is to introduce this equivalence graph, which keeps tracks of equivalences, and then have a separate data structure for tracking congruent terms. And this equivalence graph is a directed graph where the vertices correspond to terms and edges corresponds to a proof of two terms being equal. And here the directions just correspond to the direction of an equality, meaning that we can flip an edge if we want to by using symmetry. One important property of this equivalence graph is that a weakly connected component will have a representative term, just like in a union find data structure. And then to construct a proof, say we want to prove A is equal to D, we will then collect the edges towards this representative term for each of the terms and then combine all of them into a proof. It's of course important that we make sure to preserve this representative term as we add new edges. And since they, Daniel Selsom and De Moore, have uniqueness of identity proof, they don't actually have to add every edge to their equivalence graph. So an example of this would be if we have this this example here. If we were to add an edge between A and C, so a proof that A is equal to C, we can actually skip this since we can already construct another proof that that A is equal to C along P and Q. But we are without uniqueness of identity proofs, so we might have some problems where we depend on a specific proof being in the equivalence graph. And an example of this is here, where the dependent path includes both P and Q in the type path, meaning that we need to have both P and Q part of our equivalence graph. So we need to be able to insert these edges as well. This also means that now when we construct the proofs, there might be more than one way to connect a term to its representative term. And the way we deal with this is the naive solution to just construct every possible way to reach the representative term, and then construct a bunch of proofs, and then use the one that matches the type. And the only way these proofs will vary is how the type path is defined. And yeah. But there will be some cases that are more difficult, where the type path is more complex, meaning that just adding both P and Q might not even be enough. There might be some cases where we need to compose these in a more complex way, and our solution to just generate every possible proof will actually have to also generate using cycles in the equivalence graph if we were to use this approach, since we can just keep cycling around and create more proofs. So this is not a good solution. So what we do instead is that we use this information we can see in the type path and add this to the equivalence graph as well, meaning that we will treat this composition up here as a proof of A being equal to B, and have that as an edge for itself. And we can even be smarter about this because we can have that when we later try to add P and Q, we can see that we already are able to prove that A is equal to B, and that these proofs are not directly used in the type path, at least not by themselves, meaning that we only have an equivalence graph with one edge in this case. So we can sort of have the same advantage as having uniqueness of identity proofs for these cases. And that brings me to the worst cases are then when there's a lot of paths in this type path, and all of them are distinct. Then we are forced to have them all in our equivalence graph. And when we construct the proofs, we are forced to construct every possible combination. This also means that the worst case here will be n squared proofs that we construct. Another new problem, which will become which appears when we lose this uniqueness of identity proofs, is that terms now can become congruent with themselves, since we have these non-trivial paths. So that's also something we have to take into account. Yeah, so here lastly, I'm not sure how I'm doing on time. I'm doing quite well. I just want to mention that we did do an implementation of this in Cubical Acta, using Acta's reflection mechanism, which performs quite well for what we have. We have a bunch of examples which it's able to solve in practical time. But there's still a lot of improvement to be done. Yeah. So lastly, I just want to conclude that we were able to implement this practical congruence closure in cubical ACTA, and that it also turns out that the path equality in cubical type theory is more convenient, at least for this congruence lemma, than the identity type in intensional type theory. Yeah, so that's actually all I prepared.
Okay, well, let's all thank the speaker silently. And then we have plenty of time for any questions. So go ahead, raise your hand or unmute yourself if you have a question.
Okay, I'll start off with a question. Hi, Emil. So what kind of examples can you do and which ones can't you do with this? Just curious.
So for my implementation, there's still a few minor bugs. So there will be some problems it won't solve, but for the algorithm, I haven't found any yet that it won't solve. But it is still just using it's just using the context, and one interesting extension would be to use the path constructors as well in the high inductive types, and yeah.
Right. Okay. Yeah, I just wonder if it could simplify some proofs in the library or something. If we would merge this in.
Yeah.
Yeah, that would be nice. A pull request is welcome.
Sure.
Yeah.
Yeah, I guess one thing that comes up a lot in cubical type theory, right, is that I mean, it's great that paths are naturally heterogeneous. They're like path overs, but as a result, sometimes you end up with a problem that something is not quite in the right type, or like it's a path over but over the wrong thing, or it's in one fiber and you need to spread it out to the whole to be a path over or something like that. I was wondering, do you have any that's another sort of thing. It's related to what you're talking about, but you could imagine trying to have some algorithm that tries to do whatever squash or transp or things like that. Any thoughts?
Yeah, I'm not sure it would I'm not sure how we should take that into account as well. Yeah. I think I have to research that a bit more to be able to say something.
Mm-hmm. Yeah. Well, I'm not sure how much one could expect to be done magically, but that's the sort of thing that ends up being painful sometimes.
Yeah.
I have a comment I'd like to make. This regards actually the second statement on the slide there. So there's some related work by my student Luis Gocola, who was able to implement in Lean generating path congruence lemmas automatically just using the usual identity types by analyzing the context and figuring out the dependencies. He didn't get as far as implementing the congruence closure part of what would be needed to actually use it for something, but he got the part that generates all the lemmas. So there is some work there that it would be great if it was complete, but in any case, it is possible to do the lemma generation without using cubical techniques.
Yes, Dan, I'll ask you a follow-up question. So Yeah, so the Celsum and Demora is also in lean, I guess, right? But the difference would be that Luis's work is not assuming UIP or
Exactly, it's compatible
Okay.
with univalence. Yeah, I should
Right.
have said that explicitly.
Just to help Emil answer the question, we did start looking at the work by Louis, and then we were actually very surprised that in cubical type theory, this actually becomes completely natural. Whereas even if you're doing the work by Louis is very impressive, but even if you look at the simple case in lean where you have definitional UIP, things get complicated. And then in cubical type theory, as Emil showed, it's what is the 7-character proof of the crucial H congruence. So that's really the big surprise. So, and that I think is the difference with both of the work of in lean and the work by Louis. Does that answer the question then?
Well, I didn't really have a question. I just wanted to point out that there is other work too that I wanted.
We cited in the abstract, and we should have put it on the slides. Thanks.
Yeah.
Any other questions? Yes, did you link to GitHub in your slides? I don't remember, but I know that your work is on GitHub, right?
There's a link in the abstraction, in the abstract, but not in the slides. No.
Anything else? Anyone? You know, the funny thing, while you're on this slide, the funny thing about like congruence laws and Funnext and so forth is in cubical type theory, it's often much harder to write the type of these lemmas than to actually prove them.
Yeah.
So often it's, you know, easier to just inline their use, you know, rather than appeal to some lemma that you have to instantiate with 15 complicated arguments. But
Yeah, it's surprisingly, it's really nice to work with when you get used to this path abstraction.
right. Like I said, the only issue is that then sometimes you end up in not quite the right type. You know, it's a path over in the wrong way or something like that. Well, guess since it's the last talk of the day, I'm pretty sure that's right. I suppose we can conclude whenever. Benedict?
Yes. What's up? You can conclude.
Wait, shall we?
Let's thank the speaker again.
Oh, yes. Thank you. Let's silently thank the speaker again.